Welcome back. Today we are doing a really focused deep dive. We're tackling quantum theory. We've drawn this straight from the core texts on molecular thermodynamics and kinetics, and honestly, our mission is to give you the conceptual shortcut. We're not going to drown you in complex math here. The plan is to walk through the big ideas, why classical mechanics fails, what wave functions actually are, how they describe molecules. Think of it as getting the essential vocabulary in those aha moments quickly.
Absolutely. And it's crucial stuff. Quantum mechanics isn't just some abstract theory. It's really the bedrock. It tells us why atoms stick together, how molecules interact with light, what gives molecules their shape. Pretty much all properties of matter depend on it. Classical physics, Newton's laws, they just don't cut it at that tiny scale.
Okay, so let's start there. Classical physics, Newton's laws. They work incredibly well for big things, right? Planets, billiard balls. But then scientists tried applying those same rules to tiny things like electrons and energy itself, and uh-oh.
Yeah, it was a genuine crisis point around the turn of the 20th century. Things just didn't add up. And this breakdown forced, really, two huge conceptual leaps. The first one was realizing energy quantization.
Quantization, meaning energy isn't smooth.
Exactly. It's not continuous. Think about black body radiation. Classical physics predicted this ultraviolet catastrophe, basically, that a hot thing should spew out infinite energy at short wavelengths, which obviously it doesn't.
Right, that would be bad.
Very.
Huh.
Max Planck fixed it.
Yeah.
He proposed something totally radical at the time.
Yeah.
Energy isn't transferred smoothly, but in discrete little packets, quanta.
So energy is like lumpy, not a smooth ramp, but steps on a staircase.
That's a great analogy. A staircase where the step height is related to frequency delineates Planck's constant. And this lumpiness suddenly made sense of other weird observations too, like heat capacity.
Okay, how so?
Well, classical physics said the heat capacity of solids should be constant, but experiments showed it dropped towards zero at really low temperatures. Einstein applied Planck's idea. If the energy steps are too high compared to the available thermal energy, the atoms just can't absorb that energy to vibrate. So no vibration, no heat capacity.
Makes sense. And you can actually see this quantization, right, in spectra.
Precisely. Atomic and molecular spectra. You heat up atoms, look at the light they emit. You don't get a rainbow. You get sharp, specific lines of color.
Like a barcode.
Kinda, yeah. Each line corresponds to a specific energy jump. Delta E equals a 1. It's direct proof that energy levels inside atoms are restricted, discrete.
Okay, so that's energy quantization. What was the second big shift?
Wave-particle duality. This one's maybe even weirder. We already knew light behaves like a wave, diffraction, interference, all that. But the photoelectric effect showed it also acts like a stream of particles, photons.
That's when light hits metal and knocks electrons out.
Right. And the energy of the ejected electron depends directly on the light's frequency, minus some energy needed to just get it off the metal, the work function. It behaves exactly like tiny bullets of energy hitting the electrons.
So light is both a wave and a particle.
Okay. But wait, it gets better? Particles do the same thing in reverse.
Electrons act like waves.
They do. The Davison-Germer experiment proved it. They shot electrons at a crystal and saw a diffraction pattern, just like light waves.
Wow.
That's the Broglie relation. Everything has a wavelength, lambda hp dou, inversely proportional to its momentum.
Here. But we don't see baseballs diffracting.
Exactly. Because the baseball's momentum, mass times velocity, is huge. So its de Broglie wavelength is incredibly tiny, undetectably small. Quantum effects, this wave nature of matter, really only show up when things are very small or confined in tiny spaces, like inside molecules.
So if particles don't have definite paths like baseballs, how do we describe them? What's the replacement?
That's where the wave function comes in. Usually written as speed, the Greek letter psi. Think of it as the quantum state description. It contains all the information you can know about the particle or system.
And how do you find this wave function?
That's the job of the Schrödinger equation. It's the fundamental equation of non-relativistic quantum mechanics. You plug in the forces acting on the particle, that's the potential energy part, V, and solving the equation gives you two things: the allowed energy levels, E, and the corresponding wave functions, C.
So it's like the quantum version of ESMA. It tells you how the system behaves.
In a sense, yes. It governs the wave function. But the wave function itself, it's often a complex mathematical function. It can be negative, have imaginary parts. It doesn't directly tell you where the particle is.
Okay, so if Hipsy isn't the position, what is its physical meaning?
That crucial link comes from the Born interpretation. Max Born figured this out. He proposed that the square of the absolute value of the wave function, C psi 2 at 2, gives you the probability density.
Probability density. So the chance of finding the particle in a certain spot.
Pretty much. The probability of finding the particle in a small region of space is CT2 multiplied by the volume of that region. We trade classical certainty for quantum probability.
Right. Now, you mentioned solving the Schrödinger equation gives you wave functions, but are all mathematical solutions physically okay?
Ah, good question. No. Because CT22 has to represent a real probability, the wave function C itself has to follow certain rules. It has to be well-behaved.
Meaning?
It must be single-valued. You can't have two different probabilities at the exact same point.
Hmm.
It needs to be continuous, no sudden jumps or breaks in probability. And it can't become infinite over a finite region. Generally, its slope, its first derivative, should also be continuous.
Okay, so these constraints, they limit the possible solutions.
Precisely. And this leads directly back to your earlier question about why energy is quantized.
How so?
Because only certain specific values of energy, E, will allow the Schrödinger equation to have solutions
Yeah.
that actually meet these physical requirements, these boundary conditions.
So the need for a sensible probability map forces the energy into discrete levels.
Exactly. Quantization isn't just assumed. It emerges naturally from the mathematics and the physical constraints on the wave function. It's a consequence of the wave nature and the boundary conditions.
Okay, we have the wave function. It holds the info. We know its square gives probabilities. How do we extract other specific pieces of information, like momentum?
For that, we need operators. In quantum mechanics, every measurable property or observable like energy, position, momentum has a corresponding mathematical operator associated with it.
An operator, like a mathematical instruction.
Yeah, think of it like that. An operator acts on the wave function. For example, the operator for total energy is called the Hamiltonian operator, often written as ast of 6. Other basic ones are the position operator, which is just multiplication by x, and the momentum operator, a Hemel-6, which involves taking a derivative with respect to x.
And what happens when an operator acts on the wave function?
Well, if the wave function happens to be a special function for that operator, called an eigenfunction, then something neat happens. The operator, acting on the function, just gives you back the same function, multiplied by a constant number.
Okay.
That equation looks like omega sena. Omega is the operator, is the eigenfunction, and omega is the constant, called the eigenvalue. And that eigenvalue, omega, is the precise single value you will get if you measure that observable property, omega, when the system is in this state.
Ah, so if terabatterly is an eigenfunction of the Hamiltonian operator, then the eigenvalue is the system's energy, E.
Exactly. Happy C. That's just the Schrödinger equation again. And importantly, for these operators to represent real physical measurements, they need a property called being Hermitian. That guarantees the eigenvalues, the measured values, are always real numbers. You can't measure an imaginary momentum, for instance.
Okay, but what if the wave function isn't an eigenfunction of the operator you're interested in? What if momentum, say, doesn't have one single definite value?
Then you can't predict the outcome of a single measurement with certainty. If you measure it many times on identical systems, you'll get a range of results. What you can calculate is the average outcome over many measurements. That's called the expectation value, usually written as Langle omega wrangle. It's the closest quantum mechanics gets to a classical value when there's uncertainty.
Which brings us to the really mind-bending part, the Heisenberg uncertainty principle.
This is fundamental. It puts a hard limit on what we can know.
It says you can't know both the position and the momentum of a particle perfectly accurately at the same time.
That's the gist of it. There's a trade-off. The more precisely you know the position, the smaller delta x, the less precisely you know the momentum, the larger delta ps, and vice versa. Their uncertainties multiplied, delta p delta x, have a minimum value related to Planck's constant.
Why? Is it just about clumsy measurements disturbing the system?
No, it's deeper than that. It's inherent in the wave nature. Position and momentum are complementary observables. Mathematically, their operators do not commute. That means the order you apply them matters. If operators don't commute, the properties they represent cannot simultaneously have precise values. If you have a state with perfectly defined momentum, like a free particle wave, its wave function is spread out over all space, meaning its position is completely uncertain. Perfect knowledge of one ruins knowledge of the other.
Okay, let's make this concrete. Let's apply these tools, Schrödinger's equation, boundary conditions, to the simplest possible confined system, the particle in a box.
Right, this is the classic textbook example, but it shows the core principles beautifully. Imagine a particle that can only move back and forth along a line of length L, and it hits impenetrable walls at either end.
So the potential energy is zero inside the box and infinite outside.
Exactly. Which means the wave function must be zero at the walls and outside. That's the crucial boundary condition.
And applying that condition to the Schrödinger equation.
Immediately forces the energy to be quantized. You find that only certain wavelengths, and therefore energies, fit perfectly into the box, like standing waves on a guitar string. The allowed energies are 1 area equals N2H2, 8 millilol2, where M is the mass, L is the box length, and N is a quantum number 1, 2, 3, and so on.
Okay, so confinement leads directly to quantization. What else does this simple model tell us?
Two really important non-classical things jump out. First, look at the lowest energy level when N1. It's E dollar equals H2, 8 millilol2, 2. It's not zero.
The particle can't just sit still at the bottom.
Nope, that's the 0-point energy.
Mm.
If the particle were perfectly still, zero momentum, we'd know its momentum exactly zero, and its position somewhere in the box fairly well. That would violate the uncertainty principle. So it must retain some minimum kinetic energy even in its lowest energy state.
Okay, what's the second thing?
Look at the spacing between energy levels. It depends on LL22. So if you make the box bigger and bigger, make L very large.
The energy levels get closer and closer together.
Right. They become almost continuous. This is the correspondence principle. As the system approaches macroscopic size, the quantum prediction smoothly blends into the classical prediction, where energy seems continuous. Newton's laws are just the large-scale limit of quantum mechanics.
What about 2D or 3D boxes, like a cube?
Then you need quantum numbers for each dimension, say 6L, NZ, LA. And something new can happen. Degeneracy.
Degeneracy.
Means different wave functions. Maybe one wigglier in the X direction, another equally wiggly in the A direction can happen to have the exact same total energy. So EACE2 and 2ANO22 might have the same E in a square box. Degeneracy is usually linked to the symmetry of the system. A cube is more symmetric than a rectangular box, so it has more degenerate levels.
And one more weird quantum thing emerges here. Tunneling.
Ah, yes. Tunneling is deeply non-classical. Imagine the particle in a box, but the walls aren't infinitely high, just a finite energy barrier. Classically, if the particle's energy E is less than the barrier height V, it can never get past. It hits the wall and bounces back.
Quantum mechanically.
The wave function doesn't instantly drop to zero at the barrier. It decays exponentially inside the barrier region. If the barrier is thin enough, the wave function can still have a small, non-zero value on the other side.
Meaning there's a chance the particle just appears on the other side, even without enough energy to climb over.
Exactly. It tunnels through. The probability is usually small, and it drops off very fast with the barrier's width and the particle's mass.
So lighter particles tunnel more easily.
Much more easily.
Wow.
This is hugely important for understanding how electrons move in materials, and even for some chemical reactions involving protons, hydrogen ions.
Okay, let's shift from simple translation to motion within a molecule, like the stretching and compressing of a chemical bond. How does quantum mechanics handle vibration?
The standard starting model is the simple harmonic oscillator. We approximate the potential energy of the bond stretching or bending as a parabola for F part 1, 2, Kf by 2, 2, where Kvi is the force constant of the bond, basically how stiff it is.
Like a mass on a spring.
Precisely. Now, put that parabolic potential into the Schrödinger equation. Solving it gives another set of quantized energy levels. The vibrational energies are eV equal to 12 Mach omega. Here, omega is the vibrational frequency, related to square down now, and V is the vibrational quantum number, 0, 1, 2.
So unlike the particle in a box where energy went as $200 here the levels are equally spaced, like a ladder with uniform rows.
Exactly. A perfectly uniform ladder of energy levels. And notice again, the lowest energy state, V0 is $T, is 12 omega.
Another 0-point energy. The molecule can never completely stop vibrating.
Correct. Even at absolute zero temperature, molecules retain this minimum vibrational energy.
What do the wave functions look like for vibration?
They're interesting. They involve a Gaussian function, that bell curve shape, multiplied by polynomials called Hermite polynomials. They get progressively more wiggly as the energy level E increases. And there's a neat result called the virial theorem that applies here. For a harmonic oscillator, the average potential energy is exactly equal to the average kinetic energy. Each contributes half to the total energy of the water.
A perfect balance. Does the oscillator show any of that weird non-classical behavior like tunneling?
Absolutely. If you look at the probability distribution, say 2002, for any vibrational state, even the ground state VO0, you find there's a non-zero probability of finding the atom stretched or compressed beyond the points where its total energy equals the potential energy.
The classically forbidden region?
Yes. Classically, the oscillator turns around at those points. Quantum mechanically, the wave function leaks out into the region where phi is taller. It's another manifestation of barrier penetration or tunneling. The quantum view is just fundamentally different.
Okay, last type of motion, rotation. How do molecules spin quantum mechanically? Let's maybe start simple, like a particle just going around in a circle.
Good idea. That's the particle on a ring model,
Yeah.
representing 2D rotation. The key here is the boundary condition. As the particle goes around the ring, its wave function has to meet up smoothly with itself after a full $360 second turn. It has to be continuous.
Like biting its own tail.
Sort of, yes. This cyclic boundary condition forces the angular momentum to be quantized. Only certain wavelengths fit perfectly around the ring. This leads to energy levels that depend on the square of a quantum number Wallers, which can be 0, 1, R9, O2, and so on. Notice that the 90 means levels, except 1 up O2, are doubly degenerate. Rotating clockwise or counterclockwise with the same speed gives the same energy.
Okay, that's 2D. What about real molecules rotating in 3D space, like on the surface of a sphere?
Right, the particle on a sphere model. This is more complex, but more realistic.
Yeah.
Now, solving the Schrödinger equation yields two quantum numbers related to angular momentum. There's orbital angular momentum quantum number. It can be 0, 1, 2. And it determines the total magnitude of the angular momentum. And there's a magnetic quantum number. It can range from 0 to plus in integer steps, so $2 plus more possible values for a given dollar. It determines the orientation, specifically the component of the angular momentum along a chosen axis, usually called the z-axis.
So the dollars gives the size of the spin, and Malor gives its projection onto one direction.
But essentially, yes. And the energy levels are surprisingly simple. L plus 1, where I is the moment of inertia. Notice the energy depends only on Malor, not on Malor.
Ah, so all the $2 plus Nani states with the same dollar but different Malaus are degenerate. They have the same energy.
Correct. For rotation in free space, the energy only cares about how fast it's spinning overall, not which way its axis is tilted. The magnitude of the angular momentum itself is also quantized, Lobawar, and the z component is libstar.
This leads to something called space quantization, right? The idea that the direction of the spin is restricted.
Exactly. Why can we only know the total magnitude and one component precisely?
Let me guess. Uncertainty principle again.
You got it. The operators for the x, y, and z components of angular momentum, little ln luzzy, do not commute with each other. They are complementary observables. So if you know level s exactly, because a little s is fixed, you fundamentally cannot know little and precisely at the same time. This means the angular momentum vector L can't just point in any arbitrary direction. It's confined to orientations where its projection onto the z-axis gives one of the allowed little bar values. It traces out a cone rather than pointing to a single spot. Hashtag, outro.
Wow, okay. We've covered a lot of ground there, from the breakdown of classical ideas to translation, vibration, rotation, but it feels like a few core themes kept coming back.
Definitely. I think three big takeaways stand out.
Yeah.
First, quantization comes from boundaries, whether it's walls of a box, the need for a wave to connect on a ring, or just the general requirement for wave functions to be physically sensible. Constraints force energy into discrete levels.
Right. Second, probability rules. We lost classical certainty. The wave function squared, CP92, is our guide to where things are likely to be.
And third, uncertainty limits knowledge. The non-commutation of operators for complementary properties, like position momentum or different angular momentum components, means there are fundamental limits to what we can simultaneously know.
And these aren't just, abstract textbook concepts. They have real-world consequences.
Absolutely. Think about nanoscience. The properties of materials change dramatically at the nanoscale, purely because these quantum confinement effects become dominant. Size dictates behavior.
Or even things like quantum computing. That whole field relies on harnessing these discrete quantum states and their weird properties, like superposition and entanglement, which we didn't even get into today.
Yeah, it's where theory meets cutting-edge technology.
So let's leave our listeners with something to chew on. We talked about tunneling and how probability drops exponentially with mass. Think about chemical reactions. Sometimes a reaction involves moving a tiny proton, H plus A. Other times it involves shifting a big, heavy group of atoms. How might quantum tunneling affect the rate or even the mechanism of a reaction differently in those two cases?
That's a fantastic question, because that difference can absolutely change reaction pathways and speeds. It's a crucial detail in real chemistry, something to definitely mull over.
Indeed. Well, that's all the time we have for this deep dive into the foundations of the quantum world. Thanks so much for joining us.
My pleasure. It's always fun revisiting these fundamental ideas.